So with understanding of the second order impulse and step responses, how you derive it, okay, we'll just talk about it just now. We can actually look at the graph itself. Okay, for the impulse, okay, when you're multiplying 1 into the transfer function, okay, when you're multiplying 1 to the transfer function, okay, because 1 is actually the impulse input. So when you have the equation, this is the portion for this one. Okay, exponential portion for this one is the decay part, while the sinusoidal is the sine omega t. Okay, so this is the impulse response for second order system, and then for step response for second order system is in terms of this equation as we have done earlier. So the exponential similarly is the exponential growth of the thing, and then well, the cosine and the sine are just the sinusoidal part. So after that, with this understanding, we can understand what is overshoot. Okay, if you remember last time modeling also talk about overshoot. The stuff is all over here. Now maybe we should talk more about that. So it is the same thing. Okay, give me a minute. Okay, I have no idea what is impulse response. Is the derivative of the step response. Okay, so the step response, when you make a differentiation, you get this dude over here. Okay, you will have this equation over here. Okay, so this is just a concept. I also don't know how to explain. I'll let you know. And then and then the rest is just talking about what you have learned in modeling, how you're gonna sub in, okay, and then the damping factor, how you're gonna, you know. But what is the key thing I want you to know is that how do you know that the damping factor is considered unacceptable or acceptable? Okay, so therefore, if the theta is larger than 45 degrees, okay, so you give me a while again. The key thing I want you to know is that the overshoot becomes very significant if theta is larger than 45 degrees, which you don't want, because you don't want the oscillation to be very big. Okay, if the oscillation is very big, the overshoot is very big, you actually cause sparks or whatever to occur, and then it will not be very stable. So therefore, you try to keep it within 45 degrees and below. And then the shape of the response depends only on the damping factor, and the speed of response depends on both the damping factor and natural frequency. Okay, if you were to ask me what is the shape of the response, I would say that it is this shape. Okay, this shape itself. So okay, this shape. Okay, so how high these things oscillate and stuff like that. Okay, it depends on the damping factor. While the speed of the response, okay, how fast it will actually decay down, okay, how fast, how maybe you'll like light and then go down, or maybe okay, so maybe I should change for a while again. A damping factor that is pretty high will damp out the system, so eventually it will just die down with no oscillation. If it's a low damping factor, okay, it will oscillate and eventually decay. Okay, so this is the damping factor wise. But similarly, for if it's damping factor, okay, if this is the case for damping factor if it's high, right? If the natural frequency comes in, okay, it will actually dies down faster. Okay, it actually dies down faster, decay faster. Or if it's for the very low damping factor which is under damp, okay, it may actually oscillate a lot compared to if the natural frequency is you know, so it's about the frequency itself, the amount of cycles per time, per period. I can't explain it very properly, so for you to check it out lah. So just to the keynote is that I think the question itself in the test will ask you what is the overshoot, find the overshoot, and then which overshoot is the overshoot acceptable or not. So how do you find? So in order to find whether is it acceptable, you have to first invert arc-cosine the damping factor to get the data. If the degree itself is 45 degrees and below, so if it's below here, it is acceptable. So if it's larger than 45 degrees, you will start to zoom out and then oscillate. So we are not looking at this portion. We are looking at this. We want it to be acceptable. This portion is unacceptable. Okay, this portion is unacceptable. Well, this portion says that it's possibly acceptable. What does this mean? Okay, and under what condition does this occur? Okay, so let us look at it. So maybe you're a construction worker and you're operating a crane. Okay, so you're sitting down here, and then you're trying to move this thing from somewhere to somewhere. Okay, and you start to oscillate because when you're moving in this direction, maybe you oscillate, go up maybe more than 45 degrees, and then come down, and so this portion here is alright. Okay, so under some circumstances you can allow larger than 45 degrees for a certain period of time. Okay, but under other circumstances you cannot allow that to happen. So you have to able to articulate between whether do you accept the 45 degrees or not. Okay, so this is where you have to really decide. And then since I have a little time, so I'll just go through what is the table itself. This is damping factor. Okay, this is a table with damping factor, the 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 degree itself, the overshoot, the overshoot degree, which is what I'm talking about, which with the degrees itself that I'm talking about. And then the H is the amount of overshoot, the value of overshoot. Percentage is the overshoot. Percentage is from this point to this point. Okay, so what is the percentage? Okay, and what is and you know what is this point? So let me ask you, what is this point? So this is actually the final value theorem. Okay, final value of your system. Okay, so this is why final value theorem is very important. So the final when your overshoot from the final value, it's some percentage, right? So it's actually reflected over here. And then omega divided by omega natural frequency is just the ratio between the natural frequency and the frequency in the damping frequency. Is I also don't know what is it, but make sure that you know all these things. And then if it's larger than 45 degrees or larger than 0.707, or using this table, or perhaps the table provided in this portion over here. If it's larger than 45 degrees, if it's like this, then this is unacceptable, not acceptable. If it's there, you can acceptable. And in order to find the degree, okay, in order to find this degree, you need to have the damping factor, okay, damping factor, and then you arc cosine, okay, you arc cosine the damping factor, okay, you arc cosine it to get your degree, the degree, and then you are able to use the table to find the overshoot and damping factor and stuff like that. So with this you give me a while. So I have cleared away the definition parts, okay, decently. I've spent more than an hour, okay, on videos on these things. So these are the definitions, and I hope that you can articulate them very well, okay? It's not well, but very well. So in the future, you can actually know what and how I do things in the later parts. And then for this, it's also very important because in the later parts, we also have to use this equation. So in the next video, I'll talk about it. Okay, and I think I'll need 2 or 3 videos. So my overall length is actually longer than the actual lecture itself. So I hope that I didn't confuse anything and to actually let you understand a lot of things. So I shall see you in the next blah blah blah. Yeah, goodbye.